Christian. At least for me, it's good afternoon, everyone. So, well, Christian already introduced the title slide, so I will be talking about different topics in applying automated reasoning in machine learning. But for those that don't know me, and probably many of you don't know me, so my work is not on machine learning in the past. It has been on SAT, on constraints, on and different applications of SAT and constraints. So here I list a few topics. What happened over the last 2 years is that we have been applying what we know to explainability and interpretability in machine learning. So essentially, the challenge that we decided to face is understanding how we can apply automated reasoning and formal methods in general in machine learning. So everybody is familiar with the successes of machine learning. There are plenty of them. We have self-driving cars, the successes of DeepMind, AlphaGo, AlphaGo Zero, AlphaZero, the different personal assistants, Watson, the advances in image and speech recognition, friendly robots, and the list is huge. What happens is that while there are many successes, people acknowledge that machine learning models are brittle. This means fragile. So, and people for the last 5-6 years have been studying what are referred to as adversarial examples. So this was, I think, one of the first examples. This is a panda, and a machine learning system would classify it as a panda. You add some noise to this image, and the machine learning system will then classify the same, what for us is the same image, as a given. There are, since then, many examples have been created. So this is an example from 2 years ago, a stop sign with some patches, which the machine learning system would understand as speed limit 45. A blurred image of 20 miles per hour, which the same machine learning system would classify as a speed limit 80 miles per hour. And what people eventually conclude is that you can pretty much do what you want with this, some of these machine learning systems. So the standard pigs can fly example. So you have the image of a pig, you add some noise to the image, and the machine learning system classifies it as an airliner. Okay. Of course, some of those previous examples are anecdotal. Some others are very serious. So this is an image of skin, and which was classified by a machine learning model as benign. So it was not a tumor. By adding noise to the same image, a small amount of noise, which we cannot really distinguish, the machine learning system would now characterize it as malignant. Of course, it could go the other way around. So that is one perspective. Another perspective has to do with interpretability. So some machine learning models are interpretable, and this means that human beings understand what is going on. So decision list and rule list and decision sets and decision trees, all of these are generally accepted to be interpretable. So for those of you less familiar with these concepts, here I show a decision set. So for this data set that is shown here in the table, we can learn these two rules. If not meeting, then we take a hike. If not vacation, then we don't take a hike. Okay, for the same data set, we could learn a decision tree. Here, so meeting, if we have meeting or not, and if we are in vacation or not, and we have different predictions, whether we take a hike or not. Of course, some other models, and usually people consider these to be the most interesting ones, are not interpretable. So the standard example is I have an image of a cat, I have a neural network, and a neural network characterizes the image as a cat. So this is fine. But the question is, why does it predict the image as a cat? So what are the important features, and can we come up with general explanations? So this problem has been around now for a few years. And this is what some people understand as explainable AI. So what we have right now is, well, this is a cat, and this is what you get in most machine learning systems. And what we would like to see is, well, this is a cat, and then an explanation for why it is a cat. I should say that we are very far away from this, but this is what people are working towards. So is XAI important? And the answer is yes. If you are in Europe, we have the GDPR. And some authors believe that the GDPR entitles you to explanations in different settings. For example, if you ask for a loan, you should understand why didn't you get a loan. In the US, the same. So DARPA created this XAI program, and that's where the acronym was created. And there are efforts also similar to the GDPR in Europe. And if regulations are not enough, then we have very compelling arguments. And this is from June 2019, communications of the ACM, so which I think is a perfect example of how we can convince ourselves and other researchers that the work on XAI is very, very, very important. More to this, in Europe, there are even now what are called the ethics guidelines for trustworthy AI. They were prepared last year. There was supposed to be a new version this year. As far as I know, it's not yet ready. And inside this document, one part is the principle of explicability. And again, it makes a very strong case for why explaining machine learning models is very important. And further to all of this, there are hundreds of recent papers. So over the last 2 years, there are literally hundreds of papers on XAI. So let's now move towards the intersection of machine learning and automated reasoning. So 2 years ago, a well-known researcher said that combining machine learning and logic is a challenge of the day. And this is the image I see as mixing the two. And there are different ways we can do this. So a good number of researchers have been exploiting machine learning to improve automated reasoning, to improve the efficiency of automated reasoning. So you have heuristics, portfolios, abstraction tactics, a huge number of ideas. What we have been looking at is slightly different. So we have been exploiting automated reasoning to improve what machine learning is giving us. So verification of machine learning models, learning of machine learning models, explanations of machine learning models. And whereas the first one can be seen as a way to improve system design or simplify system design. So sometimes it is difficult for humans to pick the right automated reasoner configuration, and machine learning here can be very useful. On the other hand, what we have been doing is to exploit automated reasoners to build trust, to help debug, and to support decision making. So what we are doing in this research project, ANITI, one of the areas is DeepLEVER chair. So we are targeting explanations, learning, robustness, and fairness. And essentially, we are trying to ask and answer some which we think are important questions. So what is a rigorous explanation? I'll try to explain what we see as an explanation. Also, there might be many explanations, so which ones to compute? How can we compute rigorous explanations efficiently if possible? How can we measure heuristic explanations? Because sometimes rigorous explanations might be very difficult to compute. We would like to offer guarantees when we compute heuristic explanations. And then another recent topic is tractable explanations, meaning that we can compute explanations very efficiently. And a long-term project is high-level explanation. So we'd like to abstract away from the features we start from, but this is yet a work in progress. We have also covered learning, and so people, a good number of researchers, some of the work done by ourselves is learning decision trees and decision sets, and I'm going to talk a little bit actually about answering some of these questions. So synthesis for robustness and synthesis for fairness. So essentially here what I'm saying is we are going to learn such that, for example, we have fairness. And another topic we started working on is fairness. So it's a fundamentally important topic. And I'm going to talk a little bit about this. So which fairness criteria to use, what is bias in the data set, when is a model fair, and then I'll show very nice connections, at least in the talk, links with explainability. Robustness is in the paper, which I mentioned here, but I'll show some links with explainability. And finally, we have verification or robustness, as it is usually called. So here, the grand challenge is that I will talk, if I have time, I'll talk about this in the end. So efficiency is a huge problem. And the grand challenge is how can we have more efficient reasoning when analyzing machine learning models. Another topic we are looking at is instead of plain neural networks, alternatives to neural networks. Very well. So the talk today is, well, if we have time, I'll cover 5 main topics. So a little bit of preliminaries so that we speak more or less the same language. And then the largest part of the talk will be on explainability. And then a little bit on fairness, time permitting learning interpretable models, so learning decision sets and decision trees. And finally, just a few comments on robustness. Again, this reflects the work we are doing, and I as far as I understand, most of the talks we essentially cover what researchers are usually working on. So in terms of preliminaries, I will talk about what problems in machine learning we are looking at, and then a very quick comments on logic and encodings with logic of machine learning models. So we are going to talk about, throughout the talk, of classification problems. We have a set of features, just numbers, and each feature takes values from some domain DI. And we are not going to, well, when we have restrictions, we will mention them. Features in general can be categorical or ordinal, discrete or real value. And given the features, we can define feature space, which is the Cartesian product of the different domains. And we can view the machine learning model as computing a classification function. So we map feature space to some classes. And for simplicity, in the talk, I'm going to usually focus on plus and minus as the classes. And for a given instance in feature space, we get a prediction, which is computed by this function, and the prediction is one element of the class. And of course, I'm assuming it is a function. I will usually use instance. It can also be called example or sample, and essentially all of this is just a point in feature space. Whenever it's convenient, I can see a point in feature space as a set of literals where I pick a variable denoting that dimension, and then equating to some value in feature space. Okay, and in the specific case of Boolean features, I will use not xi and xi when the values are 0 and 1 respectively, and this is standard. Okay, very good. So in terms of logic overview, I'm going to talk a little bit about entailment because again, I don't know the background of the people that are attending the talk. So let's first understand entailment and then we take it from there. So we have some formula phi defined on feature space, and we associate the same name to the function. So the function maps feature space to 0, 1. This is not a limitation. I will explain how this can be generalized. Let's consider another formula, again, defining another function. And we say that the second formula, tau, entails phi, and this is the notation that we use, if for all points in feature space, if tau holds, then phi holds. Okay. So let's see a concrete example. Suppose I have 2 dimensions, Boolean features. So the function is x1 or not x2. And as long as x1 is true, then the function is going to be true. And if not x2 is true, then the function is also be true. So this is just to illustrate entailment. I should have another example, slightly more complicated. Now three dimensions, x1, x2, x3. I have x1 and x2 or x1 and x3. And as long as x1 and x2 is true, then the function for sure is going to be true. So we can say that x1 and x2 entails the function. And x1 and x2 are the same. If we have non-Boolean feature spaces, we can just define a predicate where we use phi c. So this is a parameterization such that phi c equals c. And it can take values in 0, 1. Why did we talk about entailment? Because we are going to introduce prime implicants. Again, I'm going to introduce also prime implicates for completeness, but the talk is, I will talk a lot about prime implicants. So a conjunction of literals pi And whenever I need it, I will use it as manipulate it as a set. Is a prime implicant of some function if the conjunction of literals entails the function, and we talked about this in the previous slide, and for any subset of literals, entailment is not preserved. Okay. So, for example, again, from the previous slide, the function with 3 variables, x1 and x2, or x1 and x3. And so we saw in the previous slide that x1 and x2 entails the function. So if x1 and x2 is true, then the function is going to be true. So this is well, I'm not proving, I'm just arguing that it's a prime implicant. And a subset, which would be, for example, x1 is not a prime implicant. So observe that if x1 could be true, but if x2 and x3 are 0, then the function is not true. So x1 does not entail the function. Okay. And the same holds for x2. For prime implicates, we use a disjunction of literals, and then it's similar, but the order here is reversed. Again, for explanations, I'm going to use this more often. Just for completeness, I added this one. Now, tools that we are going to use and assume that are known. So SAT reasoners. So SAT is the decision problem for positional logic. We use conjunctive normal form. We can solve different optimization variants, max-SAT, pseudo-balloon optimization, min-SAT, and so on. And there are quantified versions. QBF is the best known. We can also optimize with quantification. We can talk about SNT, which is the decision problem for decidable fragments of first-order logic. And also there are optimization variants and there are quantified variants. And we can also talk about mixed integer linear programming. So here we have conjunctions of linear inequalities over integers or real valued variables. And finally, I'm assuming all of you are familiar with constraint programming. Sorry, mistake. So I was assuming that there was a lecture on SAT and SNT, so I don't really have a lot to talk about SAT and SNT. I and colleagues have given lectures in the past, so there are here 2 links in case you want to go and check what in case something is not clear, but I would assume that it's not really a problem. So why do we need logic? So one reason is that we need to represent machine learning models with logic so that we can reason about them, right? So I will start with a very simple example. So suppose that you have 2 features. So they are integers, for example, 0, 1, 2, x1 and x2. And then I create 2 rules. So if 2x1 plus x2 greater than 0, I predict plus. And if 2x1 minus x2 less than or equal to 0, then I predict minus. Now, so again, this is a really simple example. I'm going to ask a question which shows why do we need to reason about these things. So a natural question would be, can I predict for some point in feature space, for some instance, plus and minus at the same time? So this is an example of what is called overlap, right? It's a fair question. And in this case, again, I was too quick. So I would like to, everyone that is attending to spend some time thinking whether this is possible here or not. Again, I already showed you the answer. So the answer is, of course, there is a solution. Why? Because if I put 0 here and 1 here, I respect the 2 constraints. And so I'm going to predict both plus and minus. Okay. So the example itself is not that interesting, but we can formalize it with logic. So I have a variable pick positive if this one is true, and pick negative if this one is true. And I want both of them to be true at the same time, right? And then I can, because I have linear inequalities, I just call an SNT solver. By the way, here it's not completely enough. I would have to put a restriction on domains, but just to give you an idea of how this works. Okay, and of course there is a solution to this if and only if I really can have a point predicting both plus and minus. A more serious example are decision sets, and a lot of people use decision sets. One reason being that they are considered to be interpretable. So here I restrict the features to be Boolean. And I have 3 rules, x1 and not x2 and x3, then I predict plus. And they are in order, so there is no order. X1 and not x3 and x4 minus, x3 and x4 minus again. So, and the same question can be asked: can the model predict plus and minus for some instance in feature space? And giving you a few more seconds to think about. We can see that yes, for example, I can satisfy the first and the third. So with 1, 0, 1, so this is everything is going to be true. 1, 1 is going to be true. So I'm going to predict plus and minus at the same time. Now the formalization here is a little bit more complicated. Again, all the variables are Boolean, so I can pick plus with the first constraint, and there is only one. So this is the constraint. I can pick negative here, and that's the constraint, or I can pick negative here, and that's the constraint. And if I want to pick positive, I need, well, the only option is to pick the first. But if I want to pick negative, I can pick the first or the second. And of course, I want to pick both because I want to have both plus and minus. In this case, things are a little bit easier because I can use a SAT solver to solve the problem. Now, again, I was assuming some background. Classification essentially is the process by which I start from here and I get a bunch of clauses. And this is pretty standard to do. We can use what's called Criterion encoding, and we will be done. Very well. So, of course, everybody would be saying by now that, well, decision sets or linear inequalities are not that interesting. We want to see neural networks. Everybody wants to see neural networks. So let's see neural networks. So again, I'm going to assume a very simple model just to illustrate the point, but it would apply in general, model being able to reason about it. So we see each layer of the neural network as a block, okay? And the first layer is just inputs, okay? And what we do, it's not shown here, it's going to be shown in the next slide, is that we are going to compute in two phases. So in the first phase, we are going to compute an intermediate vector given the input vector in this case, and then we have a matrix of weights and some bias vector. And then we compute the actual output given this intermediate value and some activation function. And we are going, as usual, to use the ReLU activation function, which is shown here. I proposed 10 years ago. So I presume this is clear. Again, feel free to ask questions. If I see them, I'll try to answer immediately. Otherwise, I'll give you time for questions later. So what I've shown, essentially what we can model this as follows. So the intermediate value is the matrix of weights times the input values, and then plus the bias. And then the output itself is the max between each of the values and 0. Why? Because of the ReLU activation function, right? So if it's negative, I cut it out. And so how do we move from here to, well, up here I'm saying I'm going to use mixed integer linear programming. I could be using SMT as well. There is no difference because SMT is a superset of MILP, at least in terms of modeling capability. So what I do is as follows. So I'm going to, can be viewed as a summation. So I'm going to represent the summation as shown here. And I'm going to use two positive variables, the y, which I want at the output, and some slack variable. And the idea is as follows. Depending on the z, and the z can only take value 1 or value 0. If it's 1, then I is less than or equal to 0. And since it's greater than or equal to 0, it's going to be 0. Otherwise, zi is 0. And in that case, it's si that it's going to be less or equal to 0 and greater than or equal to 0. So it's going to be 0. So what I'm saying is that either yi is positive or si is positive. Now, let's see what happens. Suppose that this value is positive. Well, there is a way to satisfy this, which is this is positive and this is 0. And this takes exactly the value of the summation, which is what I want. So I'm in the second part of the ReLU activation function. Now, suppose that the summation is negative. Okay, in that case, the only consistent solution is to put this to 0 and put this to the same positive value as shown here. Essentially, I'm just putting the value somewhere, and at the output, I'm going to put 0. I presume this is clear. Again, this is not the easiest or simplest encoding, but the other ones, as far as people are aware, are not as effective in practice. Okay. Now, again, I've seen over the last 2 years many people saying that, well, if logic is a limitation when you are reasoning about machine learning, and that is really not true. So it's essentially you give me or any researcher that is familiar with logic any machine learning model, and we can model it with logic. And usually it's a simple process, as I tried to convey over the last few slides. Because I'm going to mention this later, for example, boosted trees are also easy to model. I'm going to do this very, very, very quickly. So the number of trees, again, for a boosted trees, if you have M classes and you have Q trees per class, then this is the total number of trees. And for each tree, what you do is you just represent, so that this path is going to be activated if all the literals are true. So essentially, this is, you can represent this trivially in logic. And so the output value, and for a boosted tree, it's going to be some real value. It's going to exist if the path is activated. Okay. So if the path is activated, then we have the real value. And then you just need for a boosted tree to sum and then take the max. That's it. Okay, so it's also easy to do. Okay, so I will give you a few seconds if anyone has questions regarding this first part. Otherwise, I'll move to the second part. Okay. Sure. So someone is asking, how about the encoding activation functions like hyperbolic tangent of softmax? Again, as long as you can use nonlinear, you can model in logic nonlinear arithmetic. So that's not a problem. Now, there is a problem, of course, but it's not a modeling problem. The problem is computational. So it might be hard to solve in practice, or the complexity of the problem might be too high. But in terms of modeling, you can do it. Okay, very good. So if not, there are no more questions. I will go to the second part. So the second part is explainability. And again, I have a bunch of topics to talk about. So I'll first try to convey what we view as the formal definition of explanation. And then explain how we can do this in practice, number one. Then assess heuristic explanations. So I'm going to show you, to convince you, hopefully, that what people have been using as heuristic explanations are problematic. And then I will talk about tractable explanations. And the reason for this is because we have a very rigorous way to model explanations, but in practice, it can sometimes not be very efficient. And I'm going to talk about tractable explanations because these are special cases which we can solve efficiently. And some of them are very practical. And then I'll show a connection we observed last year between relating explanations and adversarial examples. So again, here for simplicity, and essentially for simplicity, I will assume categorical features. Again, the same framework as before. Again, the same domains and feature space as well. And for convenience, the classification function will be called the model of the point. And again, I'm just going to assume two classes for simplicity again. And the prediction will be as before, and I have what will be called the prediction literal, which is true whenever the function computes the class. Okay, very good. And I can also, because I'm going to work with this later on, I can see the point as a bunch of literals, as a cube, a conjunction of literals, such that some variable for some coordinate takes the value of where I start from. Okay. So why is this important? Because what I'm going to show in the next slides is how we can essentially capture the problem of finding an explanation and proposing a definition of explanation. So the input, in this case, the example I showed before, the image, I'm going to represent it as C. And this is to be consistent with the previous slide. Okay, so these are essentially all the literals describing the input. And this is why I call it the cube. And now the machine learning model, and again, this is the justification for the M, is going to be represented called M. And again, I showed before, we can encode it with, depending on the type of machine learning model, with SAT, SMT, mixed integer linear programming, whatever. Okay, and given one of the questions, we could also use some fragment of first order logic. Of course, we would pay the price in terms of computation time, but we could do it. And finally, the output, in this case, it's cat. This is my literal. Okay, so this is the class I predict, and I want to. So I'm going to be happy if the prediction is kept. So when I'm going to try to explain what is going on. So what do we know? We know that if we are given the cube and the model, then we get the literal, so the class C. And what we did last year was relate the explanation with something which has been done in AI for many years, which is propositional reduction, which essentially computes explanations. So we have a bunch of hypotheses. In our case, are the literals at the input. We have a theory. In our case, it's the encoding of the machine learning model. And then we have a manifestation. In our case, it's what we are predicting. And we want to find some subset of the hypotheses, so of the input, such that I'm consistent with the model, and what I pick and the model still entails the prediction. So the first part is, in this case, easy, trivial, because it's a tautology. It's also guaranteed to be true, so we don't really need to care about it. And we can do some transformation of the second part. So this part, we can transform it such that we want the set of literals that we are going to pick to entail that the model implies a prediction. So what we are saying essentially is that the set of literals that we are going to pick is a prime implicant of this function, this modified function, which we can view as a decision function, where the model implies the prediction. And and that also explains why I started the lecture by talking about entailment and prime implicants, because we used it for explanations. So we can use subset or cardinality minimal. We can compute both. Again, there is a difference in cost, and I'm going to talk about it. And this is what we see as an explanation. We call it, so we have different names for this, but it's the name that I'm going to use more often during the talk is prime implicant explanation, or PI explanation. And a number of authors over the last year and a half have been really putting effort trying to be able to compute efficiently PI explanations or prime implicant explanations. Now, this is a very strong statement. What I'm saying is that for any instance that is consistent with the subcube I'm picking, and given the model, I'm going to guarantee that the prediction is going to remain unchanged. Okay, and we are going to see more examples throughout the rest of the lecture about this. So in terms of computing just a prime implicant, it's just a subset minimal explanation, and it's very easy to do in practice. So we just need to be able to run entailment checks. And I talked about entailment at the beginning of the lecture. So as long as entailment, if I take the literal and entailment is preserved, then I drop the literal. And I do this through going over all literals of my input cube. Okay, so notice that this runs in polynomial time on the number of features. Of course, the entailment check could be very hard. Usually it will be NP hard, but it can be done. Okay, and again, for those of you familiar with the advances in SAT and SMT solvers and MILP and CP, you know that in many settings this can be computed efficiently. Now, usually computing cardinality minimal explanations is much more complicated. So usually, for example, if you are modeling neural networks, for example, or decision sets, whereas entailment checks is co-NP complete, this is going to be hard for the second level of the polynomial hierarchy. So it's a much harder problem to solve, and that also shows the more complicated pseudocode. And just to say that we still have the entailment check here, but to search for the minimum, what we are going to do is iteratively compute a minimum hitting set. If we have entailment, we are done. If not, we block this solution and look for another one. So essentially, this is the grand idea of this loop. This looks very simple, but in practice, it's, as I said, quite much more complicated. And I'm going to show you some results. So, but again, we can prove that this gives you a smallest prime implicant and so smallest explanation. Okay, very good. In general, and I'm going to show you some results, we target minimal conditions that are sufficient for the prediction. So as long as I have those literals, I'm going to have the prediction. And so, to be very clear, I'm equating explanations with prime implicants, and this is, as far as I know, the most rigorous way of defining explanations for some function which is modeling some machine learning model. So what we are doing is essentially picking a subset of literals such that the entailment is still preserved and its subset minimal is set. Okay. Notice that we were not the only ones to think of this. So actually, we did it in. It's not shown here, but so we did it in beginning of 2019. Some others did at the end of 2018. So equating prime implicants as explanations with prime implicants was proposed in compilation-based approaches. So the idea here is fairly different from what we do in terms of how you how do we put in practice the procedure. So whereas we use NP oracles, as I just showed, this alternative approach compiles the representation of a decision function and then finds a prime implicant. Okay, we are going to use throughout the talk the name PI explanation. Again, PI means prime implicant. Again, I showed this slide before just to say that because I'm going to show you some results. So this is, we start from the neural network. We know how to do the encoding, mixed integer linear programming. And these are the results we obtained last year in 2019. So these are data sets, number of features in each data set. Here is subset minimal explanations, cardinality minimal or minimum explanations. The dash means we cannot compute. And again, as I said, this is if the decision problem is NP complete, then finding a minimal prime implicant is going to be hard for the second level of the polynomial hierarchy. So this is essentially, this is the reason for that. Now, whereas computing subset minimal explanations is usually feasible, again, the number of features is not huge, but it's usually feasible. Notice that this is for a neural network. We are computing explanations when we pick a neural network to represent these data sets. Sorry, let me go back. What we observed is that for this concrete problem, neural networks, and only for neural networks, mixed integer linear programming is faster than SMT solving, as you can see from most of the results. And here it scales better, okay? In terms of explanation size, we can go from very small explanations to, well, large explanations, but as you can see, there is a reduction in general, on average, a reduction of the number of features, total number of features to the explanations that we compute. Okay. Now, as I said, these were neural networks, and so this was, as far as I know, the first rigorous approach for explaining neural networks, computing prime implicants of the decision function associated with neural networks. Now, this is the positive aspect. The negative aspect is shown here. It scales to a few tens of neurons. Okay, and so that is where a huge challenge is. So, again, we can do a few tens of neurons. The best that exists in terms of reasoning rigorously about neural networks is a few hundred neurons. This is not for explainability, it's for robustness. So this essentially says that if we want to do explainability with a better engine, we can probably go to a few hundred neurons, but that's it. And that is where a huge challenge currently is, okay? And that's why this is what motivates the rest of this part of the lecture. Okay, very good. So let's, what we did also, besides showing that we can compute prime PI explanations of neural networks, what we did was measure how good heuristic explanations are. Why? Well, if you go and check the work on these explainer tools, Lime, Sharp, and Anchor, you'll see that they are highly visible. So they have had a huge impact. And so what we set out to do is understand whether these explanation approaches heuristic explanation approaches offer any guarantees of quality. And so I'm going to show you two scenarios under which we measure the quality of heuristic explanations. Okay, very quickly. So Lime and Sharp share some similarities. They learn a very simple. So you start from, for example, a neural network, and you learn a simple interpretable machine learning model. So, for example, linear classifier or the decision tree. And the difference is, whereas with Lime you train the classifier, in Sharp you use game theory to learn this classifier. So LIME is sample-based. You try a large number of samples. SHAP, if you want to be exact with SHAP, depending on the model, it can be sharp p hard. So if you want to be rigorous with SHAP, it's going to be much harder than what I showed before. And anchor is slightly different. So instead of learning an interpretable model, it just learns the features that can be considered the more relevant for the prediction. And again, anchor is also sample-based. So none of these tools offers guarantee of rigor in the computed explanations anyhow, okay? So let me, one of the first experiment we did was the following. So we want to measure the overall quality of heuristic explanations, given that we compute that heuristic explanation somehow with anchor or LIME or SHAP, okay? So what did we do? So we learned a machine learning model. So we used XGBoost, and we learned boosted trees just to show as the exercise. Okay, we could have used others, but here, as I'm going to show, we got much better scalability. And then we compute a heuristic explanation using LIME or SHAP or anchor. And then we use what the process I described, so an abduction-based approach, to measure whether the heuristic explanation is really an explanation, a PI explanation or not. And if it is not, then we fix the explanation. So we use, for example, anchor or LIME or SHAP to give us an explanation. And then if it's not a PI explanation as we define it, then we fix it. And in this case, we say that explanation is incorrect. Why? Because the set of literals that we obtain is not sufficient for the prediction. If the explanation holds globally, but it has redundant literals, then we can refine it. So we just take literals that are irrelevant. And in this case, we mark the explanation as redundant. So the set of literals is sufficient for the prediction, but some literals are really not necessary. And finally, if the case 1 and case 2 fail, then we say that the heuristic explanation is indeed the PI explanation as we defined it in this lecture. Okay. Now, why do we use boosted trees and not neural networks? Because here we can really scale to very realistic sized boosted trees. So the ones used in Kaggle competitions, for example. Okay, very good. So, so this is for those of you which might not have understood the complete details. So we compute an explanation. For instance, just to illustrate the point with anchor, we check with our tool whether the explanation is correct, and then if the explanation is correct, we refine it if necessary. If the explanation is not correct, then we repair it and find a correct explanation. So just to give you an example, this is a very simple data set available on the machine learning repository. So it's the Zoo data set. And this is a simplistic boosted tree just because to fit the slide. So we have 7 trees, and depending on the value, we pick the class. Okay, so the class can be amphibian, bird, bug, fish, invertebrate, mammal, or reptile. Okay, and we went to the data set, and this is a concrete example. So if it's the animal name is pit viper, it doesn't have hair, not feathers, eggs, not milk, and so on and so on and so on, then it should be classified as a reptile. Okay, now what we did next was we gave this to anchor. And the anchor replies that, well, for this example, it's not air, not milk, not tooth, not fins is an explanation. Again, and this is what anchor says, it's an explanation. And so it's essentially, from a logical perspective, what we are saying is that as long as these literals are true, then the class should be reptile. Why? Because in the previous slide, I showed it was reptile. Okay? Well, the problem is that even in the training data, so it's not test data, it's just training data, there are the same explanation incorrectly classifies another instance. So we have another example where the class should be amphibian and the same literals are true. Again, so but if we use the explanation of anchor, we should be saying it's a reptile. So that would be incorrect. And so this is what we got. We considered 5 data sets. And so this is the percentage of incorrect explanations that we got, redundant explanations and correct explanations. And so the numbers are in red because they are frightening, in my opinion, at least. So this is of the explanations that we computed with Lime, 94.1% are not correct. So they don't entail the prediction. 99.4 here and so on. Okay, Sharp is slightly better than the other ones, but in any case, the numbers are, so with the exception of lending data set, in all the other data sets, most of the samples that we considered, we were getting incorrect results. So the explanations that these tools compute are not sufficient for the prediction. Okay, and we show that actually, usually if they get it right, and they usually don't get it right, then there is not much redundancy. Okay, and one of the reasons is that these tools usually are quite aggressive. They propose very short explanations which are not correct. Okay. By the way, there is a Google XAS service that, as far as I understand, is very similar to Sharp, at least in terms of its principles. So this is more or less what you would get in terms of the correctness of explanation when you compare it with PI explanations of a tool like Sharp. Okay, so that was the first experiment, and as I said, it's not really positive. The second experiment was, so one thing is, can we break the explanation? And we can. The second is, how often are heuristic explanations really consistent? So it could be the case that we were just lucky, and in many other cases, or most of the time, it would be consistent with the prediction. So this is another work we did. And so what we did here is we needed a different setup, and I will explain why. Because we need to use model counting. So we need to look at all the possible feature space and then count when it's correct or it's not correct. And so the only way we could do this was to use a SAT-based encoding. In this case, we used binarized neural networks, a fairly well-known machine learning model. And then we computed heuristic explanations with Anchor. Again, we got similar results with Lime and Sharp as well. And then because of the difficulty of the problem, we use an approximate model counter, and then to measure how often the explanation is consistent with the prediction. Okay. And again, we did not get good results. So this up there, the three continuous lines are up here. This is what Anchor believes are the precision of its predictions. And this is what we measured. So for example, we have examples where the number of times, the percentage of times it's correct, it's less than 40%. Okay, and in most cases, it's really well. So we tried 300 examples. Clearly, here we still are with most of them are below the 80%. Okay. So whereas Anchor usually finishes saying that it's 99% precise, the explanation, these results show it's really not the case. It's very different, the scenario. And so we think that these results really underscore how it is important to have formal explanations, so PI explanations, for example. So sorry for the long stretch. If you have questions, I'll give you some seconds to pose them, and then I will move to another part of the lecture. Okay, there was good. There was one question. Well, yes. So the question is: so CM is to be seen as a set of representing formulas that for sure lead to the right classification. It's not. I would not see it like that. Essentially, is like you suppose you have your machine learning model. You put what is in CM in the right inputs. No matter what you put on the other ones, you are going to get the right prediction. So that is the vision I'd like everyone to convey to everyone. So essentially, what we are saying is that the ones we are not we are dropping, we are getting rid of, can take any value. Okay, but these ones have to be fixed to what was given when we started to compute the PI explanation. Hope this is clear. Okay. Oh, there is another question. Well, so the question is, many thanks for debunking some of the hype of these tools. Have you contacted with authors of them? No, we have a report that is available. Nobody likes to see negative results. So it's really a very negative result. But we have had these results available on archive for more than 1 year, I think. Yes, close to 1 year. So again, notice that this is not, the tools are not incorrect. So it's not, again, I don't want to convey the wrong impression. The tools are correct. They are just, they have no guarantees of rigor. Okay, that is what I'm trying to say. Yes. So another question, I was wondering how you train Lime and Sharp for making the explanations in the experience, because they are designed to be, okay, so what we did was we compute, because they are designed to be local methods. So try, yes. No. This is for a specific instance. So it's really what they are targeting. What could be criticized is that they really don't compute an explanation. They compute an interpretable model. So it's a linear model. And we use the literals that they are given, or most of the literals that are given. And so it's pretty rigorous what we did. Okay, but thank you for the question. It may be a problem between the equivalence of the encoding and the SAT encoding. I don't really understand the question. So for the counting, no, because the counting does not depend on the encoding. So we may actually got this question by some reviewer some time ago. No, it's not a problem, but this is a very good question. So it's really, so there are possible criticisms of the work that the last part that I showed. But it has to do with, because the approximate model counter itself is not that rigorous, might not be that rigorous. So the guarantees are not, it depends on the type of problem. But again, it's not certainly the problem of the encoding we are using. Okay. So if we were to spend more time, the guarantees would be stronger, but then we'd have to spend much more time, and that is the problem. Okay, I will continue. Because, well, I think some of these questions might appear later again. So very good. Thank you very much for the questions. So again, after talking about formal explanations and assessing heuristic explanations and being very clear that in some cases, it's very hard to compute explanations because, again, we are solving an NP-hard problem on a machine learning model that could be very large size. I'm going to talk about 2 examples of tractable explanations. So I would like to start with a teaser, which is, so I started by saying several times that we want interpretable models. Decision trees are examples of interpretable models. So a question we came across some time ago was, so do we need PI explanations for decision trees? So let me convince you that we do, actually, we do. And it's a problem, it can be a problem. So suppose you have this instance, this is a decision tree for some function, which we don't know, it's a black box, the function itself. And we consider the input all ones. So it's highlighted here, the path in the decision tree. So the prediction is plus. So x1 is 1, x2, okay. This, nothing like, okay, this should be a 0, but everything else should be a 1. So it's fine. It doesn't change any, well, it doesn't change the prediction. Actually, it should be here, but I want this path because, well, just to illustrate the point. Okay, so this should be a 0, everything else is okay. So when we compute the PI explanation, essentially we are asking the question, why is the prediction plus? Okay, so essentially we want to compute the PI explanation for this prediction, given the instance, and here again should be 0, okay, because of x2. Okay, now let's analyze this, and let's say, so I would ask everyone, and if anyone wants to reply, otherwise I'll give you a few seconds and I will give the answer. So prediction, will the prediction change if I allow x1 to take any value? So right now it takes value 1. Suppose I allow it to take value 0 as well. Will the prediction change? Okay, nobody is Q&A, but again, I'm assuming someone, yes, no? Okay, so, oh, actually someone said no, thank you. And it may change. So, well, the first one was right, the second one was not so right. So the answer is no. Wait, let me go. Let me go back. So it's no, because notice that since x3 and x4 are 1, I'm going to force the path to come here, no matter the value of x1. Either comes here or comes here. So the value of x1 is really not important. So again, some of you might have seen it. So the prediction changes if x2 and x1 can take any value in 0, 1. Let me see if yes or no. Okay. Oh, there was an answer, two answers. No, doesn't matter, exactly, very good. So it really doesn't matter. So the value, I can put any value next to the next one, any value, it doesn't change because no matter the path I pick, I will end up here, okay? And the same here, right? And here is what, that's why, yeah, it should have been 0 here. But anyway, so let's continue. So it's no, and so the PI explanation for, in this case, it's as long as x3 is 1 and x4 is 1, the prediction is going to be plus. Okay. So what we actually proved recently is that there are these functions for which the path can grow with the number of features, as in this case, and the PI explanation has constant size. This is, you could say, oh, but this is a concocted function. In general, this is not the case. I'll show results that it actually sometimes happens. Actually, quite often it happens. So we have to take time. So let's first, there is a question immediately. Model refining. Well, again, I'm not sure if I'm familiar with model refining. So here, this decision tree is minimal. You cannot, we can prove that you cannot simplify it. Again, you can change the order, so you don't get this path, you'll get some other path, but it's going to be, there will be some path. That is the point. Yeah, there are no redundant literals really. So this is really a minimal decision tree. Very good, very good, very good question. Okay, so let me continue because this is, I think, actually, thank you for the very insightful question. So let me go and what we noticed, actually, we decided to go and check the books. This is what you do when you come across something that is puzzling. So we checked the Russell and Norvig book, and well, the problem is there. So this is much more complicated to analyze. But so this is patterns, hungry, type, and weekend. Okay. And so if I did not make a mistake, it should be full, yes, tie, and no. Okay. So the prediction is no. The question is, what is the PI explanation in this case? Or otherwise, can you get rid of literals? And the answer is, again, I hope some of you can see that the value of hungry is irrelevant, because if it's no, the prediction is no. If it's yes, well, because if the other ones are fixed, I'm going to get no anyway. Okay, so here I can come to yes and drop it, and so a PI explanation will be full, tie, and no. And there are more examples in this example from Russell and Norvig. Okay, so if anyone is getting furious with me, please don't, and please feel free to ask questions. Okay, so if you don't like Russell and Norvig's book, that's fine. We have more examples for you. So this is Zhu's book on ensemble methods, and a very simple example. And let's consider a PI explanation for this case, which I hope it's correct. So is y greater than 0.3? No, so we are here. Is x greater than 0.64? Yes, so it's cross. And so if I ask you for a PI explanation, anyone, if you are quick enough, what is the PI explanation in this case? Or the question is, do I need the two literals for explaining why I'm going to predict cross? Okay, someone, just why exactly? So someone immediately saw that just why? No, why is not important, actually. I think that's what you were trying to say. Why is not important? Let me, I am not, just x, exactly. Very good. Several people immediately said yes, because as long as x is greater than 0.64, again, I don't care. If y is greater than 0.073, cross, fine. Otherwise, it's no, fine, but then because of x, it's cross. So essentially here, the PI explanation would be just x. And notice that this example is also interesting because it really does not matter. So here we are using real valued features. It doesn't matter, okay? Again, I define this for Boolean variables, but we can generalize it for real valued or integer valued features. Yes? Okay, so let's see another example. Oh, sorry, this is another example. This is from Alpaidin book, 2014. And again, it's essentially the same example. So I hope I don't have to spend a lot of time on this one. Here, again, this x1 is not important. X2 is enough. For this, in this case, as long as x2 is 0.87, so here, the value of x1 is not important. And again, if none of these examples convinces you, from Poole and McCarthy's book. Actually, here it was easy to spot two examples. So this and this. If it's this one, you can get rid of that one. If it's this one, you can get rid of that one. Of course, I'm picking small examples because they are much easier to analyze, but this applies in general, okay? And so what I'm trying to say is that, well, most of the books we could come across, the trees that they use have this problem. So the paths will not be PI explanations. And again, this is inherent to the way you represent classification with decision trees. Okay, very good. Oh, there is another question. Okay, very good. No, this was just an answer to a previous question. Okay, so let me give you a little bit more insight. So how do we compute explanations? So an easy way to compute explanations would be, well, I explained to you how this could be done several slides back. So we just encode the problem in logic and use in this case, we could use a SAT oracle. Worst case exponential time, but it can be done, okay? Now, the interesting part is that notice that actually here it's like we are trying to cancel paths. So if I want to get prediction plus, what I really need is that I need to ensure that all the negative paths are going to remain inconsistent. So I want to drop literals and guarantee that I still, the only path that I can still get to will predict plus, okay? So this essentially can be mapped into finding a subset minimal hitting set of all the negative paths. So if I have the negative paths, I want to still hit them, all of them, such that they are inconsistent, and this guarantees that I'm going to get to plus. And finding a subset minimum, not the minimum, just a subset minimal hitting set is known to be solvable in polynomial time. So what I'm trying to say here is that for decision trees, I can compute explanations in polynomial, one PI explanation in polynomial time, okay? Now, of course, in some cases, this is a little bit more complicated, not in terms of the complexity. The algorithm has to be a little bit more complicated because there are tools which check variables multiple times along a path. And our report talks about all of that, okay? So just if you are not a believer, just by seeing what the examples I showed you, these are a bunch of data sets. And so these are two tools. I cannot actually see them. So IAI is a commercial tool developed in the US by a company called Interpretable AI. So they pride themselves on having producing interpretable decision trees. And ITI has been around for many years. It's well known, highly tested. And I would like to highlight, again, there is a lot of data in the slide, and I would like to highlight some points. So the percentage of redundant, percent R means the percentage of paths that have redundancy. So you can drop literals. So it can be very small in some cases, but it can also be very, very large. So this means that 80% of paths in the decision tree that we get for mushroom with IAI, interpretable AI, 80% of the paths have literals that you can drop when we are computing an explanation, a PI explanation. And the same is true across the board for ITI, okay? As you can see here, we can get, I think we get even larger numbers. We get 80 for sure, yes. I thought 87, yes. So that's one aspect. The second aspect is, okay, if you have redundancy, how many literals are you getting rid of? Because of course we could have a lot of paths where we are getting rid of literals, but it's just one literal, right? And so a second metric is, what percentage of the literals in the path are we getting rid of? And as you can see, it's not that small. Okay, sometimes it's on the tens, but it can go up almost to the 40s. I think here, 37 here, yeah, right. And here I think it's even, yeah, you can get even larger. So this means that more than 50% of the literals, on average, this is on average on the path, you can drop them for a PI explanation. So it's pretty neat, I think. Okay. Very good. So what do I have? Do you have questions on decision trees? Okay. Okay. So if not, I'm going to proceed. Very good. So this is one example of tractability. The second one, we are going to present it at NIPS in a couple of weeks. And again, it's the same setup, but in this case, we are going to consider naive-based classifiers and linear classifiers. Actually, most of these slides are on naive-based classifiers, but the same ideas apply to linear classifiers, okay? And so again, we want to compute PI explanations. And here I have another example just for those of you that may want to catch up. So I have another example of a classifier. Well, this is just the feature space, but the classifier is here. So I predict plus and minus depending on the same relation. If it's greater than 1 plus, less than or equal to 1 minus. And if I have 2, 0, then the prediction is plus. Okay. And the P explanation in this case is, we can conclude that the value of x2 is really not important, no matter the value that you put, because since x1 is 2, this is 4. So it puts at such a higher value that the value of x2 is irrelevant, essentially. Okay. So the rest of these slides, I'm going to consider that the prediction is plus, just to make it simple. We could do the same analysis for minus. Okay, so plan for these slides. I'm going to talk about naive-based classifiers. Again, some of you will be very familiar, some others not, probably not as much. And then I will use an intermediate representation, which is convenient, and then introduce some notation that we need to use, and then show that if you do all of this, you can compute PI explanations of naive-based classifiers in polynomial time, log linear, almost linear. And you can enumerate explanations also in log linear time. So log linear delay, meaning the time in between computing explanation is log linear. Actually, it's linear, but we say it's log linear because of the first one. Okay, so this is for those of you familiar, and this is an example of a Bayesian network, and it's a naive base. It's well, depending on the classification, it's a naive base classifier, but it's because the features we assume conditional independence given the class, the goal here. So the way we represent the naive the Bayesian network is we have the probability for minus, and given the class, which can be plus or minus, we have the probability of each of the features R1, R2, R3, R4, given the class. And if we are given some evidence, we want to pick the class such that maximizing the probability. And for those familiar, this is the expression. So we use conditional independence such that we can compute the probability of C times the probability of the leaves conditional to the class. Okay. And well, it's a standard transformation, at least for the last almost 20 years, is that we can just apply logarithms, and we also do a translation, not essential, but it simplifies analysis. So we can still compute the argmax, but instead of having a product, we just have a summation. And because we are doing logarithms here, we can, instead of using probabilities, we use log probability, shown here. And so we just have to pick the argmax of computing a bunch of log probabilities. And so for this example, let me show you concrete. So we have this instance. So here we have 1, 0, 1, 0 shown here. We have the probability for plus. Usually it's not shown because it's implicit. So it's 0.1, it's shown here because this is 0.9. And then we have the probability of R1 given the plus, 0.95. So essentially this table is taken from the Bayesian network. So the probability of not R2 given plus, it's the complement of this one, so 0.95, and so on and so on and so on. So we can just use these values. Let me go back to compute these sub-expressions, and then pick the max. So in this case, the probability of log probability of plus given the input 1010 is 1347, and minus given the input is 1041. So the bottom line is that I'm going to pick class plus. Okay. As I said, I'm going to focus on class plus, but the same analysis could be done if it was class minus. In this case, it's going to be class plus. Very good. So what we do now, what we want to do essentially, the grand objective here is how do we offer an explanation to the user if he's looking at a naive-based classifier with not 4, but 50 features or 100 features. Okay, so this is the exercise I'm going to go over in the next slides. So what happens is that, again, look, reasoning in terms of argmax is hard. So we are going to do a bunch of transformations. Again, they are not very hard, but please bear with me. The objective is just to show you that the steps are small, easy enough, and show you the different steps until we get to the result. So again, this is the standard definition. This is what we did, and this is where we are. What we are going to show you is how we go from this, which looks difficult to analyze, to something which is, I'm going to show you, is much easier to analyze. So it's a summation. This is for real valued features. In case I have a linear classifier. So in this case, I'm not going to pay attention to this part. I'm just going to focus on naive Bayes, and I'm going to use this sigma, which is just saying that I'm going to select, given the evidence J, I'm going to select one of these. So EJ can take one value from its domain. If it's the first value, it's this one, the value I'm going to use. Second value, and so on. Okay. So, for example, if I have here, I have 0 and 1 as possible values for R1. So I have only 2 values. If it's 0, I pick this one. If it's 1, I pick this one. Okay. And so what I'm going to show you is that I can go from this complicated expression with argmax to something which is going to be much easier to analyze, which is this XLC. XLC means extended linear classifier, because I can handle linear, and I can handle this extended part, which is I use to model naive-based classifier. Okay, so how do we do to eliminate the argmax? So what we do is we do essentially, instead we pick plus if the difference of plus with respect to minus is greater than 0. So this is what I write here. So I want the difference between the plus and the minus to be greater than 0. And then I'm going to aggregate terms because, again, I have Boolean features. I'm going to aggregate in terms of the positive literal and the negative literals. Okay. Again, this is simple. And now to map to the extended linear classifier, I just have to say which of these parts is what. So W0 is going to be this part. V1 is going to be this value here, because it's for the value 0 of the literal. And the second value, V2, is this part for the positive literal. Okay, so essentially, by doing this transformation, I went from the argmax for the naive Bayes to an extended linear classifier. Okay. Very good. So now here I show how we can compute the different values. So here I put all the probabilities. I'm not going to go over all of them. Again, it's a simple exercise. So the bottom line is that if I have all these values, then I can compute the translation to the extended linear classifier. Okay. Again, given the expressions in the previous slide. Okay. So for example, W0, let me go back. So it's W0 is going to be the difference between the log probability of plus and the log probability of minus. So I have here the log probability of plus minus the log probability of minus, and I'm going to get this value. And so on and so on and so on. Of course, some of the other ones are a little bit more complicated, but they are just differences anyway. So I have them here, I just have to compute them, okay? And so now I have an extended linear classifier. And if I have an extended linear classifier, then let's first define what we call the gap value. So this essentially is how much I am positive, how much I'm allowed to get rid of while still being positive. So I'm going to compute the value, and I want that value to be greater than 0. Okay. Well, it's greater than 0 because I'm predicting plus. And another value I need is the worst case gap. So essentially, for each feature, I'm going to pick the worst possible value. And again, it should be negative. Otherwise, if everything was positive, then I would never change the prediction. So I start by saying the prediction is plus. And in the worst case, well, it should be negative to change the prediction. And what I essentially need to do is play such that I go from positive and stay positive and get rid of some features. That is the objective. Okay, so now I can relate these two, and essentially I rewrite one in terms of the other. So I will use a different name because it's convenient in terms of talking about these things. So this one is shown here, so I can expand, and then isolate terms and get the gap value. Okay, and then I introduce a new variable, which is the delta. It's a local gap for each feature between the value it's taking given the evidence and the worst case value. Okay. And I continue. So in the worst case, so if I'm going to get rid of features, I want to pick a set of features that such that I'm still positive. So these are the ones I'm going to keep. The other ones can take any value, and I want still to be positive. Okay. And so this shows how I can compute the different, given the XLC, how I can compute the different deltas and the value itself. Okay. And so this is just showing how each value is computed. The color code shows how each one is computed. And this essentially, I can now formulate this optimization problem, which is I want to find the smallest possible value such that I'm positive. So meaning I'm still predicting plus. Now this looks like, but it's a different case of an EPSEC, and we can solve it in log linear time. And another observation that we made is that not only we can compute it in log linear time, the first explanation, we can enumerate any explanation with log linear delay. Okay. And so here we show the example. So we can compute, we sort the deltas, and so we can look at the sum. So notice that essentially I'm summing. Let me go back. So I need to do the sum such that I'm comparing with this, and this was shown 2 slides back. So I need to be above this value. So if I drop this one, I'm still fine. If I drop this one, I'm now greater than. So this is I need to fix these two, and these ones I don't really care. Okay. So the PI explanation is if I have this one and this one, or in the first this feature is true and this feature is true, then the value of these other two features is irrelevant. Okay. So is this important? And the answer is yes. So I'll try to explain with some experimental results. So so this is the tool we implemented is XLC, the name, explanations for XLC. And this is the performance. So here what we did is we considered 80,000 instances for the data sets, large number, all the data sets we could get our hands on. We modeled them with naive-based classifiers, and then we compute for each one 1 million explanations. And this is the time we need to compute 1 million explanations. So if we have less than 1 million, we stop, of course. And in some cases, we cannot stop because there will be more than 1 million explanations. So as you can see, in most cases, we can compute 1 million, even if we don't stop. So this is 0.1 second, 1 second, 10 seconds. So in most cases, it's almost instantaneous to compute not 1, but 1 million explanations. So this is the performance of our tool. We compared with STEP. So this was a tool proposed for naive-based classifiers two years ago. And this is a compilation-based approach. So you compile a representation and then you compute the PI explanation. And so these are the results for this tool, for STEP. So the reds means memory outs and timeouts, again, because since you compile, the tool is worst case exponential in space and time. And so you can see that 19 and then 9, so 27, you cannot finish, so you cannot even compile. For the other ones, you can. And so for these ones, we show here the comparison between our tool and a STEP. Okay, computing again 1 million explanations. And as you can see, our tool is usually faster, but here it's not really as significant. What is significant is that in most data sets, you cannot the naive-based classifier that you get, you cannot compile to a canonical representation which you can then analyze. Okay, questions? Oh, sorry. Yes, questions? Okay. No, that's the point. So the question is, so you have to compile the NBC to a logical representation. So in this case, well, it's not, right? So essentially, we just do a transformation. We move from the naive-based classifier to an extended linear classifier. But it's just, there is no, there is a logical analysis, but the representation is just a few differences, okay? So, So essentially what we have to do is compute the quantities I showed. So the gap value, the worst case gap, and then the deltas. And then with that, you can then plug them to the algorithm and which it's shown in the paper. Again, the slides don't show the algorithm, but it's really not, it's very simple. And then you can, depending on the number of explanations, it will go through and give you the explanation. But by the way, something I did not mention is that the first explanation is guaranteed to be the smallest one in this case. So everything is in P. Okay. Okay, very good. Something else I had that we did last year is we noticed the first connection between explanations and the adversarial examples, and I would like to share that with you. So this was presented last year at NIPS. There is as I said at the beginning of the lecture, a lot of work on computing explanations. Again, a lot of heuristic work, but also some recent rigorous approaches. And of course, needless to say, there is a huge amount of work on adversarial examples. And the question we asked ourselves was, can explanations and adversarial examples be somehow related? And actually, it was a coincidence that the recent work, when we did this last year, they had observed that there seemed to be some connection, but there was no formal evidence. It was just some comments in some papers. And so we show that there is really a simple connection to start with, but I think, honestly, I think there is much more to it, which we have not yet come around to extend. So what we did is show that there is some eating set duality between almost, well, one of them and the other, and which essentially this builds on the work of Reiter from the 80s. So I'm going to use a very simple example because, again, we could do this. It really does not depend on the model, what we are going to talk about, but I need a model to show you some examples. And so I'm going to pick from Russell and Norvig the standard restaurant example, which I already talked about today. And so this is taken from the book. Again, you have a bunch of samples or instances, and these are the features I also talked about a little bit more than what I showed before. In this case, I am showing everything and whether we wait or not at the restaurant. And so, by the way, just for those of you that might not be that familiar, A will be alternate, bar, weekend, hungry, patterns, some people inside or not, the price, expensive or not, rain, if I have a reservation, the type of restaurant, and the estimate of time that I need to wait, okay? And so some of these features are, well, I'm going to use just literal. Some of them are naturally Boolean, some others I'm going to show literals by using equality, for example. So alternate, yes or no, bar, yes or no, weekend, yes or no, hungry, yes or no. Patterns can be, there can be different sum, full, and empty, I think. Price, if it's raining, reservations, so on and so on, okay? And so if I start from this data set, so this sample example data set, I can, with an off-the-shelf tool, learn the decision set. For example, this is one possibility. So I have 5 rules, and 2 predict that I'm going to wait, and 3 predict I'm not going to wait, okay? And so again, this is very similar to what I showed at the beginning. In this case, applied to the restaurant example. And so if for example, if there are patterns and the estimate time is not greater than or equal to 60 minutes, then I'm going to wait. And again, this is going to be consistent with the instances for which this is true, okay? And I have another rule for yes, a little bit more with 3 literals. And then I have 3 rules for no, okay? So for example, if it's not weekend and it's not true that there are some patterns, then I'm not going to wait, okay? And so on and so on and so on. So very good. So what is a counterexample? So again, notice that I'm going to relate with the notions of subset minimality that I introduced before. So a subset minimal set of literals is a counterexample to some prediction if that set of literals entails a different prediction. So it's one of the classes and it's a different class from what I started from. Okay. A break is, we say that a literal breaks a set of literals, and where, so here each set of literals is denoting some feature, if the S contains a literal that is inconsistent with that literal. Okay. So let's see some examples. We are going to consider prediction yes. And if you recall, there were two rules for prediction yes. So we're using rule 1, and if it's a consistent instance, so the explanation will be just the literals of the rule. And a counterexample would be something that is different. So either this literal is different, or this literal, in this case, let me go back. Okay, otherwise this is not clear. So I have, what I'm going to do is pick this one here, this rule here, and this rule here. So this is what I'm going to show here. So a counterexample for predicting yes would be a rule that predicts no. Okay. And so if I have a set which is that set here taken from this rule, which is shown here, so it's going to break the counterexample, this one here. Notice that this literal is inconsistent with this one, and so on. Okay. And so what we proved in this paper last year was the following. So every explanation breaks every counterexample, and every counterexample must break every explanation. So this is the first part of duality. And so because of this, we can compute explanations from the counterexamples by using set dualization, so which I mentioned before, and vice versa. So I can compute the counterexamples from the explanations. Of course, usually it will be much easier to compute explanations from counterexamples, not, of course, for decision sets, but for example, for neural networks. And given some instance, we can compute adversarial examples from the closest counterexample. So if I have a counterexample, then I can find an adversarial example, meaning I need to specify all the literals such that I get a different prediction. Okay. And so just to show how this works, I have the restaurant data set. Again, the model is the decision set I showed before, and the prediction is weight yes. Okay, so I have two explanations. Why? Because I have two rules, and I'm assuming I cannot simplify them. And I have three counterexamples, so each is one of the other rules which predict no. And again, we can do this by hand, so we can show that each counterexample breaks one of the explanations and vice versa. So are there questions? Okay, very well. So the third part is on fairness. So this is work we did this year, and it came as a surprise because first we are going to analyze a concrete criterion for fairness, and I'm going to talk about it shortly. But what we notice is that there is a connection between fairness and explanations as well. And so this part of the talk will be understanding fairness, so just the questions we are interested in, the criterion we studied, and then how we can relate fairness with explanations, and finally, how can we learn fair models? Okay, so let's start. So the questions we started from are, what criteria should we use for fairness? And I'll talk about this shortly. How can we measure what is the criterion for dataset bias, and what is the criterion for fairness for a particular decision? So is a decision fair or not? And how can we learn a fair model even if we have a data set that has bias? Okay, and I'm going to show you in a few slides an example where we did exactly this. Okay, so again, notice that here we are going to introduce a slightly different notation because we need to talk about different types of features. So we have the non-protected features, so features we are not interested in, so salary, age, car brand, and so on. And then we have the features that are protected, and those are the sensitive features. So gender is an example, race is another well-known example. And so we define the classifier as a function on two sets, non-protected and protected features. And the data set will also be characterized like this. So it has, we have the non-protected, the protected, and the classification itself. We are going to assume it's 0, 1. It really does not matter, okay? So we of course we have standard examples. Should we approve a loan, and we want to make sure that it's fair, the decision, so there is no bias. And should a judge release a prisoner on probation? This is a very sensitive example, and I will talk a little bit about this one later. So let's talk about the concrete criterion for fairness. So it's called fairness through unawareness, and informally. Fairness through unawareness says that the decision function should be a function only of the non-protected features. So it should not depend on the whys. So we can model this informal criterion in logic as follows. So so if this fails, then it will not be fair. So we can test unfairness of the model as follows. So I'm looking for some non-protected feature such that there are two different protected features. They are different, and the prediction is different for the same protected values of the protected features. So what I'm saying is that the function behaves differently on if I fix the non-protected features, it behaves differently given the protected features. So a concrete example, just to make sure this is understandable. Alice and Bob, for example, everything is identical about them, and Alice is refused the loan, but Bob is not. So again, here the protected feature would be gender, and clearly, if everything else is equal, the decision was made on a protected feature, meaning gender. Okay, we can do some optimizations. I'm not really going to talk about them. And of course, a lot of people have and will continue to criticize the fairness through unawareness, FTU, because there are clear examples. So there might be correlations between protected and non-protected features. So for example, a bank might not be unfair to women, but they don't give loans to people that are pregnant. Simple example. And sometimes discrimination is actually good, and FTU does not model that. So, for example, if you are using height to pick people for the army, women should be positively discriminated. Of course, it makes sense. Okay, and so we can several things. Let me go back. So again, even with all this, we used FTU, number one, and number two, we are going to argue that FTU is actually quite nice. But let me first talk about, we can use FTU as a criterion for dataset bias. So we have a dataset, and we would like to see if there is bias in the dataset or not. So again, we just have to look for a set of non-protected features and two different protected features such that they are different. And I have one at 0 and the other one at 1. Okay, and if this happens, I have bias in my data set. Okay, and notice that this does not here. I'm where is it? So I'm not asking that this is a function. It could just be a relation, meaning I could be predicting for the same input on protected features and unprotected features and protected features, and get the different predictions, again because the data set has inconsistencies. Okay, and if we use hash tables, actually this can be very efficiently implemented, and we can do this in linear time. Okay, very good. Going back to the criterion, so if what we showed in the paper is that if we come up with a bunch of 5 quite fairly reasonable axioms for a criterion, which we call coding independence, monotonicity, non-arbitrary, discerning, and simplicity, we prove in the paper that the only criterion that satisfies the 5 axioms is FTU. So what is the point of this? It's just saying that even though it can be criticized, it's a fairly good criterion for a criterion for fairness. Okay, and that's essentially, this is the main result. Now, the point I would like to, given what I talked about until now in the lecture, is how can we relate fairness with explanations? So let's see an example why this can be important. So we consider a lady, Emma, and she wants to know why she was refused a loan. if she was refused a loan because she's a woman. Okay, and the bank is actually using a very simple model. So they refuse a loan if the client is unemployed or if the client is a woman. Of course, there is bias here, right? So it's very unfair because it's going to use gender to reject a loan. So in this case, the bank claims that the decision is fair because they refused the loan, given that Emma is actually also unemployed. And Emma argues, well, there are actually two explanations, because I'm unemployed, but also because I'm a woman. And so she thinks that the decision should be considered unfair. So the question is, who's right in this case? It's not an easy question. And this leads us to a few additional concepts. So again, this is the PI explanation, which we have seen several times. Again, we need, this is modeling entailment, the entailment condition. And just another example so that we are familiar with the notation in this concrete setting. So we say that an explanation is fair if so notice that now I'm back to explanation. So an explanation is fair if it includes no protected features. Okay. And so this leads us to two types of fairness of explanations. So this prediction is a prediction for some input, some class, is, we say it's universally fair if all of the explanations are fair. Okay, so any explanation that I can compute is fair. And it is existentially fair if at least one of the explanations is fair. So why is this interesting? Because in the case of Emma's, the decision is existentially fair because it is fair in one example, but it's not universally fair because, as Emma points out, she could have been refused because she's a woman. Okay, and why this is interesting also because this raises questions in terms of computational complexity. So checking fairness of a model is in CoNP. So whether if it's all the decisions are universal fair. Checking essential fairness is in CoNP, and checking universal fairness for a given decision is in the second level. Notice that we are not proving hardness. We are just saying that we can model it in the second level. We don't have an hardness result. Okay, but again, it seems reasonable to be in the second level. So just a comment on learning fair models. So the idea is as follows. We want to learn a machine learning model that it's going to be fair. So the protected features are irrelevant. Okay. Now, if the data set is biased, we are going to pay the price in terms of accuracy. We are going to lose some accuracy because we need to discard those examples essentially, and we are going to predict incorrectly in those cases. And we use a majority vote solution. So since we are going to compute a machine learning model, and that is a function, what we do is we pick the prediction that maximizes, picks the most common class as I change y and I fix x. Okay, so essentially I'm saying that it does not depend on I, and I'm going to pick the one that occurs more often for y when x is fixed. And so this means that we allow, I'm going to talk about this shortly, we allow even sacrificing even more accuracy to get a model that is simple for the user. Okay, so what the example we did is as follows. We learn a Boolean function given some sample, and we are going to make sure that it's fair given the way we construct it. Okay. And so the exercise we did was we are going to learn a decision set, so a number of the DNFs, such that each term, so each conjunction is small. So we fixed it for a small number. And then what we can do is we can model this as a SAT instance. Again, if the fourth part of the talk of the lecture will be about this. So it can be done, and the size is reasonably amenable. Given so we need to each positive example. So this is just for one DNF. We need to do this for the DNF that predicts positive and for the DNF that predicts negative. But for each one, the size is amenable. And just as an example, so the composite data set is, so essentially is measures whether a criminal defendant is likely to reoffend. So if it can, so if it's called the recidivism data set. And this data set has a lot of protected features. So one example is the criminal African American, is it Asian, is it Hispanic, and so on and so on. Okay, and it is known that the data set has a lot of bias for obvious reasons, because again this is what people have seen in prisons over the years. And so even if you want to get even if you allow for bias, the maximum accuracy that you can get will be less than 70%. Now, what we did is we sacrificed accuracy to obtain an interpretable model, and get fairness. And so, so this is what we got. So notice that it's apparent that the features that we are looking at are so the number of priors. Again, you could say, but there is some connection between priors and race. Well, yes, but again, we are assuming that that is not the case, and not some score factor, misdemeanor, age, and so on. Okay, and it's easy to reasonably interpretable, and it's not the best we could get, but it's not very far away from the best we could get. Okay, there are lots of questions actually. Okay. So the first question is maybe silly, but what about changing decision systems so they learn make decision by maximizing explainability or fairness? Well, that is a very interesting question, but okay, so that's exactly what we are doing. So essentially what we are ensuring with this the decision set approach is that we get a decision set that is fair, okay? So that's the, but again, in terms of maximizing explainability, again, that's what I think we should discuss offline. For example, let me give you for example, you could learn a neural network. And again, I'm not saying neural networks are bad, they are amazing, but then you have to pay the price in terms of explainability. You could learn a naive-based classifier, which is reasonably good, and then we can, well, it's not explainable, interpretable, but you can compute explanations very efficiently. So that would be a possible trade-off. Another example of a trade-off is that instead of a neural network, you learn a decision tree, and then you know that at least one explanation you can compute in polynomial time, and usually they are much more interpretable. So yeah, there are a number of trade-offs. Learn for explainability, I've not seen. Learning for fairness, this is what I just showed. Another question was, so we just need to ignore the okay, there were several questions. Okay, let me, so we just need to ignore the protected features while computing the PI explanation. Well, the problem is that you don't have control over that, right? So I did not mention, that's actually, thank you for the question. So this is, so asking for a PI explanation that does not have a literal is in most cases very hard to answer. So it's, so if the decision problem is NNP, most likely this question would be in the second level of the polynomial hierarchy. So if you don't want features, you cannot just get rid of them. So you might be unlucky and get an explanation that has a protected feature, number one, okay? Another question is it possible to classify specific data points on a fairness scale, or that, or that classification, or is that classification then to the data set as a whole? That's what we did. So we did a classification on the data set as a whole, for specific data points. That is an interesting concept. We did not even think about that. So I would have to sit down and look at it. It's a very good question. Okay, there are lots of more questions. So so we just need to ignore the protected features while computing the PA explanation. Again, this is not possible. In order to get fair explanation model, the model decision should be fair. It's not really correct to ignore the protected features when computing explanation, and right? Exactly. So we are not doing that. So we can, as I said, we cannot do that. So we are computing explanations given what. So you could have a very complicated model. Think of a neural network, for example, where you have protected and unprotected features, and it is such that because it's convenient, and that. But what we are looking at is we can ask whether the protected features impact any of the explanations for a given point, or whether. So it's. So I think this answers your question. So we are not ignoring it. So they could be there, they could not be important. If they are important, they will appear in an explanation. If they are not important, they will not appear in an explanation. Okay. So I think this, hopefully this is clear. Okay. Very good. I have 10 more minutes, if I understand correctly. Yes. And the point is that, well, there is a lot more to talk about. So what I'm going to do is I'm going to distribute the slides as is. So and then if you have questions over these parts, you can ask. So here, essentially, complements the part on fairness, because here we formalize how we can learn decision sets mostly, but also I mentioned learning decision trees. And so we used SAT for both. In both cases, people more recently have been using branch and bound for decision trees. Again, there are a bunch of ways of doing this. And this is what a significant body of work has been taking place over the last two and a half years. Okay, so again, I will not go over this, just to say it exists. Again, it was a lot of material anyway. But again, this was a formalization we did 2 years ago in 2018, and people have built on this since then. Okay, this was one thing I wanted to mention, and we got some preliminary results, and there are some improvements which I mentioned here as well. We also did work on decision trees, again, learning decision trees, and we showed that it was feasible. A lot more people have done work since we did it, and they improved on what we did. So again, just to say, there is a lot of research going on in these areas. And I had some comments on robustness. So that was the final part of when I started the lecture. Just so essentially here we want to prove properties of machine learning models. So there are different questions you can ask. There are different trade-offs people have been studying, where you lose soundness, you lose completeness. You try to keep both, and then you pay a price in terms of computational complexity. And just to mention, one of the best known is Reluplex. More recently, it has been renamed Marabou. And so why do I talk about this one? Because first you have an encoding of a machine learning model, and then you have a dedicated engine to reason about, in this case, neural networks. So again, it's a very active area of research. One of the challenges is exactly the challenge I mentioned at the beginning of the lecture with respect to neural networks. So we can, with our approach, we could explain neural networks with tens of neurons. They can explain, analyze neural networks with a few hundred of neurons. So this really says there is a very significant limitation at this stage in what we can do, and this is an open research. Okay, very good. So this is just the conclusions, and we have 10 minutes for questions. Feel free to ask questions. So this essentially summarizes the final slide. So I covered mostly this one, a little, mention this one, and mention this one. I think this is what we are doing and others are doing, and this is very important. So I cannot claim this is a huge success. Why? Because there are people, well, that's why we are doing tractable, for example, explanations, but scalability is important. So sometimes it's just a perception, but sometimes it is true. But as I said, sometimes even when the problem is NP hard, we can compute it efficiently. Another thing we notice is that people shy away from rigor or formal approaches. So it's very tempting to consider heuristic approaches, even when all the evidence that we have suggests that they should be doing this, because the results they could get, well, if it's just, if the machine learning model is used for some simple application, it's fine. If it's an application that could impact human lives, then if the explanations are wrong, that means you could be trusting a system which you should never trust. Okay, that's it. So I will be answering questions in case you have them. Thank you. So one question is, what do you think of logical tensor networks for your topic? Yeah, great. Very good question. Yes, we have not gotten there. So it's, as I said, this is effort for the last 2 years. So there is a lot of questions we don't have a good answer to. If you want to exchange emails and do some collaborative work, I would be more than happy. We don't have a good answer for that. Is there a way to define an order to sort the different PI explanations we have for? No, that's a very good question. So it depends on the problem. So let me try to be very precise here. So for example, for naive-Bayes classifiers, we don't have a chance. So we got a very nice result. We can do log linear delay, but we know that the first one is the smallest, and then after that we don't have any control. If you want to have control, you're going to pay the price in terms of complexity. If you are trying to enumerate explanations, for example, for neural networks, it's much more complicated. It's really much more complicated. One of the reasons is that, as far as we know, there is no easy way to enumerate explanations. Well, again, here I know more, but I'm not at liberty to talk about this because it's work under review. But so enumeration there is a big challenge. I'm at liberty to say that for sure. More questions? Okay. Oh, there is another one. Another very good question. So, what are my comments about reinforcement learning for decision scheduling? Yeah, very. Okay, so the answer is that is in our remit. So we'd like to do it, but we have not done it. The team is not well. I started full time on this 1 year ago. There is a lot we didn't have time to get to. Reinforcement learning is one such topic. So I would love to have time and people to do it, but it's right now it's impossible. So if we were to do to put effort on reinforcement learning, we would not be doing other things we think we can do efficiently, quickly, and we know what to do. So that was one question. Can you compute other types of explanations on decision trees? What do you mean by that? Again, because again, I'm not sure if I'm. Yes, I think so. I cannot elaborate on that. Again, it's not in the public domain. But yes, the answer is yes. We know how to do it, but it's not. I cannot say more than that. Sorry. More questions? If not, I will not today because of the time zone, but I will try to be available on Discord tomorrow most of the day. So as I said, someone said that I want the slides, and thank you for the other comments. I will do that for sure. Again, I noticed that there was this typo, the 1 and 0 for X2. So I need to fix it, of course, but that's the only typo I noticed. So that one I'm going to fix. As I said, the last slides, I just rushed through them, but I'm going to keep them because you can look at them, and if you have questions, you can ask. So yes, I'm going to I'm not sure if I can finish them the changes today, but I will do that during the evening, and I'll send it to Christian.
Yes, we put all the slides on the website, and also the video. The video you can be able to watch and download the video also.
Okay. Again, I will fix the slide and then I'll send it to you. Okay. More. Okay. Okay. So there is a student asking for pointers. Let's again. I don't have them on the top of my head because it has to do with reinforcement learning. My suggestion is send me an email if I forget. Otherwise, try to ping me on Discord, and I'll try to make available some pointers. I have some pointers. Again, it's not well very formalized, but I have some pointers. I can share them with you, of course. Okay, Cristian, should we give people a little bit more time, or?
Well, the session is almost finished. If you have maybe one more question, one or two, Joao can answer. But otherwise, you said you can be available on Discord at some time, maybe.
Yes, I will. Tomorrow I can do. I will try not to. Today's a little bit more complicated because of logistics, but tomorrow for sure. Okay. Again, I have some meetings in the morning. After that, I will be attending the sessions, and I will try to be on Discord as well. So if anyone has any questions, just drop me a line.
Yeah, I think this is the best way. So tomorrow afternoon, if I understand well, Joao can answer some questions on some pointers on Discord. So thank you very much, Joao, for this excellent talk, excellent lecture.
Thank you.
And
thank you.
Thank you also thanks to all the participants. You were a very huge number of participants today again. So let us meet tomorrow at 11 for the Axel Parmentier's lecture. Thank you very much, and good evening.
Thank you. Bye. Bye.